Okay, I decided I'm going to shoot a little video to show something that I read on Codebase 64 that talks about kind of a trick with the way that the REU works and how it does a triggered transfer by a write operation to the address FF00. Now that feature of the REC can be used to you basically need to have I/O mapped in so that you can write to the registers of the REC chip. But then when you go to perform the transfer, you may want to bank out I/O and then perform the transfer so that the REC chip reads from main memory in order to do the transfer. So it has a feature that when you write to its transfer register, it has a bit that lets you adjust whether you want to do this triggered transfer, and it will simply defer actually beginning the transfer until you make this write operation to FF00. Now the thing in Codebase 64 indicated that if you do an inc FF00, due to the way that the REC takes over the bus, it will actually prevent the memory address, the memory value at FF00 from being modified. Okay, so here is what we're going to do. We're going to test to see if that works. So I'm in zap REU, and the first thing I'm going to do is I'm going to clear. So I'm going to say fill value. Fill value is 0. Okay, so we're going to set our start address shall be our end address. So our end address will be bank 01. Our start address will be bank 01. Okay, so I've set our starting address is bank 01 and then memory address 0000. End is bank 01 and 00FF. Fill value of 0. So now we're going to begin the fill. Okay, that was very, very fast. Now we'll go into view mode, and we can see here that we're looking at bank 0, page 0, and everything is zeros. Okay, so that's enough for that. We've just cleared out our bank 1, page 0. Next, what I'm going to do is go into my tests here, and I'm going to launch Turbo Macro Pro. So in Turbo Macro Pro, I already have configured here a test program, and I'm just going to go briefly through how this test program works. So these includes here are to get some predefined constants for accessing the REC chip, and this include here is to give us a little basic preloader so that we don't have to type sys, but we can just type run. So the first thing that I'm going to do is I am going to clear all of memory from FF00 to FFFF. Now that's under the kernel ROM. So the moment we bank out the kernel ROM, if interrupts are still enabled, we're going to crash. So we're going to mask interrupts so that we don't get a crash. Then we're going to do a deco 1 and a deco 1, which I blogged about once. What this does is decrementing 01 the first time banks out the basic ROM. And then decrementing 01 a second time banks out the kernel ROM. So now the only thing we have in banked in is I/O, and we can leave that banked in. Next, we'll just do a little loop. So we set our accumulator to 0. We set our X index register to 0, and we start writing our 0 accumulator to FF00 at X, increment X, and until it loops over, we're just going to keep looping here, and we're going to basically fill up all the way from FF00 to FFFF with 0. And then we will inverse what we did here. So we'll just inc 01, we'll bring the kernel ROM back in. Inc 01 again, we'll bring the basic ROM back in. And then at that point we can then clear the interrupt mask. Next, now the next problem is that in most machine language monitors, they rely on the kernel. So if we use our machine language monitor to bank out the kernel ROM using this technique here, it's going to crash again. Right in the kernel ROM itself is going to crash. So we'll get to that in a second. We'll get to what we're going to do about that in a second. So the next thing we're going to do is we're going to fill up a page of memory that we're going to transfer into the REU. So we'll fill up C1 from 00 to FF. This time it's a very similar loop. We'll start with X, or X index being 0. We'll start with our accumulator being 0. But this time what we're going to do is we're going to transfer the X into the accumulator, and then we'll write the accumulator to C1, 00 plus X, increment the X register, and loop back around, except this time we're going to transfer the X register back into the accumulator, and then write that new accumulator value to C00 plus 1 instead of, okay, so now what we're going to do is we're going to fill up that entire bank with numbers incrementing from 00 to FF. So let me skip this code for just 2 seconds, and no, I'm not going to skip that code. I'll come down here to show how I'm doing the writing of the registers to the REC. So I have a little table here called REC tab, a little REC table, and these bytes correspond with the register values that we're going to write to the REC. So the first, the address of the REC chip at 00 is actually a status byte. We don't care about reading the status byte. The next byte is the command byte, and the next 2 bytes are the memory address in the C64 to transfer to or from. The next word is the address in an REU bank to transfer to or from. The next byte is the bank of the REU. And the final word is how much data we want to copy. So if we analyze this, we'll start at the bottom. We want to transfer 1 page. We want to transfer it into bank 1 of the REU. In the REU, we want to transfer it starting at page 0. But in the C64, we want to transfer it from C100, which is that sample page that we filled up earlier with the numbers that increment from 00 to FF. And the command byte here is something that I have previously defined because I find the bits hard to remember. But basically, what this is set up to do is it's going to do a transfer from the Commodore 64 into the REU, but it's not going to do it immediately. It's going to set it up for doing this triggered transfer, which is one of the bits in the middle. So here we have this table, okay? But and so now to write this table to the REU, we want to write the bytes from here up so that the last thing that gets written to the REC chip is this command byte. So all these things, all these transfer size and bank and memory addresses, they'll all be set first, and then this transfer command byte. So that's exactly what we do here. We're going to configure the REC by first loading X as the last byte in the table. So we then read the last byte from the table, and we write it to the REC chip plus 1 because the table doesn't include that read-only status byte register that we don't care about. So this will simply go grrr, and it's writing to the REC from the table, but it's decrementing the X register, so it's writing backwards through the registers, and the last register that it writes is that command byte. But it has the trigger bit set. So that means that it's not going to actually perform the trigger until we do something with this FF00 address. So now, in order to trigger the, I could actually just do this without mapping out the kernel ROM, but I'm going to map out the kernel ROM just for completeness sake. So once again, because I'm going to map out the kernel ROM, I'm going to first mask the interrupts. Deco1 is going to map out the basic ROM. Deco1 again is going to map out the kernel ROM. Now here's the trick. I'm going to increment FF00. And the test is going to be, will the value of FF00 actually get incremented? Or will it remain 0 like we set in the loop at the very beginning of this program? Now you would think that what you have to do is load the value from FF00 into something like the accumulator. Now you have a copy of it. Then write the thing you just read back to it. And then you've preserved it and you've written to it. Now the reason, actually there is a reason why I banked out the kernel ROM, is that what I don't want there to be any confusion about what it's reading. So for example, if the kernel ROM is mapped in and you do a read, you actually read the byte from the kernel ROM. And then when you do a write, it writes it into the RAM that's under the kernel ROM. And so doing an inc is kind of a weird sort of thing, right? Because you would expect that the written value, if the kernel ROM were mapped in, every time you read, you're going to read the value from the kernel ROM. And then every time you inc and then and you write it back, you're going to be writing back just one number bigger than what was in the kernel ROM. So we can ignore all that by simply mapping the kernel ROM out first. So that's what we've done here. We map the kernel ROM out. Now we're going to do this inc, but the thing is that I learned from the Codebase 64 article is that what happens on this inc is called a read, modify, write instruction. And so what it does is it performs a read, and then internally it goes through a phase where it increments the number. But during the cycle or cycles, maybe it's 2 cycles, I'm not sure, while it's incrementing the value, the original value is already on the address bus. So it's already on the data bus. And during that phase, it activates the write line. And so what happens is that it performs a kind of phantom write of the original value that was on the data bus from the read. It performs that phantom write once first, and then it takes the value that it has incremented in the ALU of the CPU, puts it on the data bus, and it performs another write cycle that actually finishes the job of incrementing. But the REC chip is listening for the write. So when the chip does the phantom write of the original value, the REC chip takes over. And when the REC chip takes over, it prevents the bus from being written to by the CPU. And so the actual write phase of this instruction fails. Now, of course, that's what we're testing, right? Now, the other problem that I mentioned earlier is that because your monitor depends on the kernel ROM, it's very difficult to read what's in RAM under the kernel ROM using a monitor, because as soon as you try to patch out the kernel ROM, the interrupts are still occurring, and you get a crash instantly because the interrupt vector has been mapped out. The interrupt vector is at the very end of the kernel ROM. So after I've done the transfer to, I've done this inc, which we hope is not going to increment FF. And the interrupts are already masked, which we can see right here. Interrupts are already masked. So before we bring the kernel ROM back in, I'm just going to take the page from FF00 to FFFF, and I'm going to transfer it to C0, page C0. Why? So that when we look at it in the monitor, we'll just see what everything in, we'll just get a copy of everything that was in FF, so that we can look at it more easily with the monitor. Okay, so we'll load our X, read from FF00 at X, store it at C000 at X, increment X, and loop to copy that one page. Next, we'll bring the kernel ROM back in. We'll bring the basic ROM back in. We'll unmask our interrupts. We'll return, and everything is done. And then we can check things out using the zap REU utility to see what's going on in the REU. And we'll use a machine language monitor to take a look at what happened at C000. Okay. So we'll get out of here and we'll load ff00 test.o, which I've already assembled. We can list that if we want. And we see this basic loader. So we will run that. Boom. Of course, it happens instantaneously, so it should already be done. So the first thing that we're going to do is we will load back in our zap REU program. Okay. And the first thing that we will do in this program is we will go into view mode. And ironically, that's actually the result of Turbo Macro Pro. So the reason I like to write to bank 1 is because, I don't know, Turbo Macro Pro messes around with bank 0. So we'll go to bank 1. And lo and behold, we cleared bank 1, page 0, and yet here we have all these numbers incrementing from 00 up to FF. So it successfully transferred our page C1, which we configured like this, to bank 1, page 0 in the REU. So that's good. Next, what we'll do is we'll take a look at, we'll run a monitor here. Okay, so we'll run this monitor, which is going to load to 2000, so it's not going to interfere with what's going on in C. We're not going to use this one because it would overwrite what's in C, but we'll use this one that's assembled to 2000. And so what we're going to do is we will look at, let's first look at C1 to C1FF. And we can see that this is the data that we configured and that we saw was successfully copied into the REU all the way up to FF. Very nice. Next, what we're going to do is we're going to take a look at our copy of FF, page FF, into page C1000 to see whether the first byte actually got incremented. And look at that. So these are all zeros because we had set all of page FF to zeros, and then we copied all of FF after the transfer to C0 so that we could take a look at it. It's all zeros, but look at this. The very first byte, which would have been at FF00, we inked FF00, then we copied it to C000. It's still 0. And so it worked. The codebase 64 trick seems to be correct. The REC prevents the inc FF00 from actually incrementing FF00. Fantastic. Thanks for watching.